Hello students, the next topic Boolean algebra, drawing conclusions, which is called syllogism. Now syllogism, what is this? This is the logical process of drawing conclusions from given propositions is called syllogism. Now in this process, the prepositions which helps you to draw conclusions are called premises. Now you need to remember this. This is syllogism and this is premises. Now there are two methods we can adopt to draw conclusions, to verify whether it's concluded or not, successfully concluded or not expression. The first method is truth table method and the second is algebraic method. Now let's try these two. The first, we have a question here on which we'll try implementing these two methods. And what the first question? The question is, from the premises P and P implies Q, infer Q. This is your question, how we are going to solve. First of all, convert this into a proper expression. What is this? P and, we know the sign of and. P implies Q. Infer means concluded, that's also infer sign will be used for that. So this statement we convert into a Boolean expression. Now if you simplify this, if you solve this and we want to check whether this is a expression which can be drawn, which we can draw successfully, which we can draw conclusions from this. So first of all is the first method is truth table. And this expression is successfully drawn or not, that depends only one thing, that the expression should be tautology. The result of the given statement should be 1. In truth table we have P and Q. You know how to make the truth values of this: 0, 0, 0, 1, 1, 0, 1, 1. P implies Q. P implies Q. If P is 1 and Q 0, then 0, otherwise 1. This rule already explained in the previous videos. And now P and P implies Q. P and P implies Q. 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. Now P and P implies Q implies Q. It means if it is 1 and that time if this term is 1 and that time if this term is 1 and that time this is 0, then whole result will be 0. So if this is 1 and that time the Q value is 0, which is not true. So when the only possibility that this can be 0 is when this term is 1 and the Q value is 0, then only it can be 0, otherwise not. So as a result you get all 1, and you have seen this statement is a tautology statement and we have successfully concluded this particular statement. Now the second is algebraic method. In algebraic method this P implies Q implies Q. We know the rule, conditional rule. Conditional rule is P implies Q is P not or Q. The first term not or Q. The conditional rule. Now we further open this statement. The left hand side term of this is the whole term not. P and P not or Q not or Q. This also conditional rule. Now P, this is break the line, change the sign, De Morgan's law. This is P naught or Q naught or Q. De Morgan's law. This is P naught. This is further apply the De Morgan's law. P naught naught and Q naught. De Morgan's law. Now P naught or P double naught is P. Which rule it is? Yeah, tell me. P double naught is P. This rule? This is involution law. This is involution law. And involution law, after this, see the P naught here and here you have P. You can apply distributive and eliminate a P term here. So P naught or P and P naught or Q naught or Q. Distributive law. P or P naught is 1, complementarity. P naught or Q naught or Q. Complementarity. 1 and this term, property of 1. So 1 will be eliminated here. P naught or Q. We know that A and 1 is A. So this is property of 1. And now in one expression you have Q as well as Q naught. So P naught or Q naught is 1. And 1 or anything is 1. That is property of 1. Identity law or property of 1. So by both methods you have seen that the statement is successfully concluded because it gives you a truth value 1, true value 1. So this is the one statement we have verified, and this statement you can also write. This statement can be written as like this also. P implies Q and this Q. So this thing can be written as this. So now here we can have another question. That question is, from P implies Q and Q implies R, Q implies R, infer P implies R. Now let's do this question. I think you can do it with the help of a truth table. That's a quite easy method. So we'll try the first one. The first method is the truth table method. First method, truth table, and the statement is, what the statement here? P implies Q and Q implies R, infer, mean this whole term infer P implies R. So there, here we have P, Q, R, 3 terms. P, Q, R. If you have 3 terms, you will have 8 combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, sorry, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 4, 0, 4, 1. P implies Q. If P is 1 and Q is 0, if P is 1, Q is 0, then it is 0. Otherwise 1. Q implies R. Q implies R. If Q is 1 and R is 0, then 0. Q is 1, R is 0, then 0. Otherwise 1. Now the left hand side, P implies Q and Q implies R. There and 1, 1 and 1, 1, 1 and 0 is 0, 1 and 1, 1. This is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Now the right side term is P implies R. P implies R. If P is 1 and R is 0, then 0. P is 1, R 0, then 0, otherwise 1. Right? So this is the answer of this particular expression. Now we write the final result here, and the final result is P implies Q and Q implies R implies P implies R. This particular expression. It means if the left hand side is 1 and this side is 0, then only it can be 0. If this is 1, if this is 1 and this is the right side is 0. The P and P implies Q and Q implies R is this, and this term is P implies this. If it is 1, it is 0, no. It is 0, no. If it is 1 and it is 0, no. If it is 1 and it is 0, no. The first term is 1, then it is not 0. Second term is 1 here, but it's not 0 here. Third term, the case doesn't arise. Fourth is 1 here, but not 0 here. The last is 1 here, but not 0 here. It means your all 8 combinations will be 1, 2, 3, 4, 5, 6, 7 and 8. All are 8, 1, and you can say this expression is also successfully concluded. And now if we simplify this by an algebraic technique, so then it's going to be P implies Q, Q implies R, implies P implies R. Apply a conditional rule. P naught or Q, Q naught or R implies P naught or R. Again open this and apply conditional. So this whole knot or P naught or R. The whole knot is P naught or Q and Q naught or R. Now apply De Morgan's rule. P naught or Q naught or Q naught or R naught or P naught or R. This is De Morgan's law. Again apply De Morgan's here. P double naught and Q naught, Q double naught and R naught, P naught or R. Here again De Morgan's law. Double naught cancel. P and Q naught, Q and R naught, P naught or R. Double naught cancel. It means involution. Involution law. Now you need to eliminate term because your ultimate goal is to get 1. So that is possible when you apply distributive, and distributive you can apply if you have joined one single term with 2 terms. So is there any advantage of joining P and Q naught with R? No, because it's a PQ and it's R. Whatever you do, terms will not eliminate. So what makes sense, you join this with this because there is a P naught and P, and join R term with this because there is R naught and R. So let's put them in a proper order because all these are in OR. It's like A plus B plus C plus D. So A plus B plus C plus D can be written as in any form. B plus C plus A plus D or D plus C plus B plus A, any. So I write P naught here and P and Q naught, R, Q and R naught. So when you change their place, this is commutative law. Now we'll apply distributive, and distributive is P naught or P and P naught or Q naught. Here again R or Q and R or Q naught. Distributive. P or P naught is 1, P naught or Q naught, R or Q, and this is also 1, and rule is complementarity law. 1 and anything, 1 property of 1, P naught or Q, and this is also R or Q, this is property of 1. Now in one expression you have Q or Q naught. This is P naught, Q or Q naught is 1 or and 1 or anything is equal to 1. That is property of 1. So by both methods you have also verified this rule. And how can we write this particular rule? This particular rule we can write here. What is this rule? This rule is P implies Q, Q implies R, and infer P implies R. So it's a P to Q and Q to R. It's kind of linked. P implies Q and Q implies R. So this is called chain rule. And the earlier we verified this rule, and this rule is P implies Q, P and P implies Q infer Q, and this is called Modus Ponens. So you have seen by drawing conclusion syllogism method, we have verified these two, chain rule and Modus Ponens rule, using both the technique, truth table and algebraic method.